Good morning, everybody. Welcome to the end of the week, December 22nd. It's Friday. It's been really unusually warm lately, which really stinks. Around this time of year, I'd really like to see some snow. But alas, here we are. It's December 22nd. The AP Calculus True Response question, Advent calendar rolls on. Let us find the 22nd compartment in this box that has served us so well for so many weeks now. Let's see. 22. There it is. There's 22. I'll zoom in for you. It's with this blue ball. There's a cute little bird. All right, more chocolate. While I open this, I will put today's free response question on screen so you can take a look. Today we're doing another kind of standard integral area type of problem. You know, we got to find an area between curves. We'll do a solid of revolution, and we'll also do one of those fun problems where the area that we're considering is actually the base of a solid, and the solid has cross sections of some particular sort. In the problem we're doing today, we're actually just given the areas of the cross sections instead of being told what shape they are. More chocolate. I'm gonna just eat meat, rice, and vegetables for all of January to recover from this. I feel so heavy. Like I go to the gym, pull-ups seem way harder than usual. It's all because of these little chocolates, I tell you. It has nothing to do with the dozens of slices of cherry pie that I've been eating. Nothing to do with that. Okay. Those red ones are so good. What's different about the red ones, man? All right, let's do the calculus. This is free response question 5 from the 2019 AP Calc AB Exam. Let R be the region enclosed by the graphs of g of x equals -2 plus 3 cosine of pi over 2x and h of x equals 6 minus 2 times x minus 1 squared, the y-axis, and the vertical line x equals 2. As shown in the figure above. So this was just a description of the region R enclosed by these curves and these vertical lines. Part A is to simply find the area of R. And note, this is problem 5. This would have been part of the no calculator section, so we will not be using a calculator for this. All right, so for part A, we're just going to have to do an integral. The integral should go from x equals 0 to x equals 2. We know that because the problem told us this region R is bounded by the y-axis, which is x equals 0, and the vertical line x equals 2. So we need to integrate from here to here. Then what we're integrating is the upper function minus the lower function. You could totally disregard which is upper and which is lower and just take the absolute value of your answer for this integral. But at a glance, you may be able to notice this is clearly the cosine function. That's g of x. That's the lower function. This one up here is the quadratic. That's the upper function. So we're going to be integrating that upper function, 6 minus 2 times x minus 1 squared, minus the lower function. The lower function is g, that's -2 plus 3 cosine, etc. It'd be great to have a calculator for this, but let's not fret. We can do this by hand without too much difficulty. Let's begin the integral. Integrating 6 just gives us 6x. As for -2 x minus 1 squared, we'll have to keep the -2, and then the power of 2 in the x minus 1 squared needs to be increased by 1. But then you also have to divide by that new power, so divide by 3. So we end up having -2/3 as the coefficient. Since we have a function inside the parentheses, we also have to divide by its derivative, but its derivative is just 1. So we're actually done with that already. Moving on to this next part, -2 is +2. So that integrates to plus 2x. As for -3 cosine of pi over 2x, we know that we're going to need a -3 sine of pi over 2x. The derivative of sine of pi over 2x is going to give us that cosine of pi over 2x but by the chain rule, it would also give us a factor of pi over 2. We need to divide that out since we're doing integration. Dividing by pi over 2 is the same as multiplying by 2 over pi. So negative 3 times 2 over pi is negative 6 over pi. So let's just put that, minus 6 over pi. And there we go. We're integrating this from 0 to 2. You might have to watch that again if you haven't practiced integration much. And if this part with the cosine was difficult, you might want to just try using u sub. Hopefully with practice, you won't use u substitution in situations where the inside function is linear, because in those situations, you just have to divide by the derivative. It's pretty straightforward, but it does take some practice. So use the u sub if you need to. All right, let's start now by plugging in this upper bound, and then we'll subtract, plugging in the lower bound. Plugging in the upper bound of 2 gives us 12 at first, so we have 12. And then here we'll have 2 minus 1 cubed, which is just 1 cubed, so we'll just be left with the coefficient of negative 2/3. Then plus 2 times 2, so that's going to be plus 4. And then with the sine function, pi over 2 times 2 is pi, and sine of pi is 0, so this whole last term is gonzo. All right, now we will subtract, plugging in the lower bound, plugging in 0. Plugging in 0 is going to get rid of that, and the sine function, because sine of 0 is 0. So all that's left is this term here. 0 minus 1 is minus 1, and then when we cube that, we get minus 1. So this should just be negative 2/3 times negative 1, which is positive 2/3. All right, now we just have to evaluate this. Let's give everything a denominator of 3 so that we can combine all of these fractions. 12 is the same as 36 over 3. Then we're subtracting 2 over 3, and then 4 is the same as 12 over 3, and then we're subtracting another 2 over 3. All right, now what does this add up to? 36 thirds plus 12 thirds is 48 thirds. Minus 2 thirds is minus 4 thirds. So this is a total of 44 thirds. And that is our answer for part A. All right, let's move on then to part B. Region R, so the same region we've been talking about, is the base of a solid. So it's like we have a solid coming up from the paper. For this solid, at each x, the cross-section perpendicular to the x-axis has area 1 over x plus 3. We need to find the volume of the solid. This is actually a really straightforward question. If the area of the cross-sections perpendicular to the x-axis are 1 over x plus 3, we just need to integrate those areas from x equals 0 up to x equals 2. So setting up this integral, all we're doing is integrating from 0 to 2 the areas of the cross-sections. That's how we find the volume of this solid. The areas of the cross-sections are given to us as 1 over x plus 3. Sometimes in these types of problems, we're just told that the cross-sections are squares, and then we could use the base length to figure out what the areas of the squares are. But this example is honestly even easier because we're just given the areas of the cross-sections outright. Now let's go ahead and integrate this. The integral of 1 over x plus 3 is the natural log of x plus 3. And we don't have to worry about absolute values around the inputs because we're evaluating this from 0 to 2, where the input of the log function will always be positive here. So let's just plug in the upper bound, that's going to be ln of 5, and then subtract the lower bound, which is going to be ln of 3. And that is the volume of the solid described in part B. Again, notice this is a situation where the inside function, x plus 3, is linear, so no u sub is really required. We would just have to divide by the derivative of this inner function. In this case, that derivative is 1, which is why it didn't really come up. Let's move on then to part C. Write, but do not evaluate. Oh good, we don't actually have to do the integral this time. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 6. Coming up to the picture provided, y equals 6 is this horizontal line here. So what's happening is our region r is getting revolved about this horizontal line, and if that happens, then hopefully you can see that this lower function, or what was the lower function, the cosine function, is going to be the outer function in the revolution. And this, what was the upper function, the quadratic, is going to be the inner function in the revolution about this horizontal line. The cross sections of this solid of revolution will be these washer shapes, where the outside is traced by the cosine function revolving, and the inside hole is carved out by the quadratic function revolving. So what we need to do is take the areas of the big circles traced out by the cosine function, and then subtract the areas of the inner circles which are removed by the quadratic function. This is a washer problem. So let's set up the big picture here. We are integrating from 0 to 2, the area of some circles minus the area of some other circles. Both of those will have a pi in them, right? It's like pi big R squared minus pi little r squared. Let's just pull a pi out of the whole thing and put the pi in front of the integral, okay? And then we're going to need that big radius squared minus the little radius squared, and this integral will be taken with respect to x. We can go back up to our picture to see what these radii are. The radius of the big circles is the distance from the line y equals 6 down to the cosine function g of x. That distance, I'll write it over here, that distance is just 6 minus g of x. That's the distance between them, which is the radius of the outer circles, or the big circles. The inner circle has a smaller radius. Let's do it in, I guess, purple. It's the distance from y equals 6 down to the quadratic function, that little distance right there. Now that distance is found in a similar way. It's just 6, the horizontal line, minus the quadratic function h of x. That's the distance between them, which is the radius of one of these smaller circles. With that, we can finish our integral setup. The big radius, big R squared, we can replace that with the radius of the outer circles, which we found to be 6 minus g of x squared. And then we're subtracting the squared radius of the smaller circles, which are cut out. That's why we're subtracting them. They are cut out from the cross sections. Those radii we found to be 6 minus that inner function h of x. Again, squared, and don't forget the dx. And there we go. That is our integral expression, which we don't need to evaluate, but just to make it very clear that all of this is in the integral, let's put it in one big set of parentheses. And that will complete our solution to free response question 5 from the 2019 AP Calc AB Exam. Let me know in the comments if you have any questions, and I really hope you've been enjoying the AP Calculus free response question advent calendar. We're really in the home stretch now, so be sure to check out the full playlist and enjoy all of the previous episodes. There's a link in the description. I'll see you tomorrow for another free response question.